So, what's up with this funky Schrodinger equation thing? Yeah, that's what still trying to figure out. But let me explain to you what I know. It's, I guess, our most modern model of electron motion and electron configuration in atoms. It's a way that we have to jive energy of an electron being negatively electrically charged and existing stable in a stable configuration around a positive nucleus. This guy named Schrodinger, about 100 and some years ago, came up with this crazy idea, based on some complicated mathematics that the total energy of the electron um, must have something to do with these possible states. E here is the total energy of the atom, and the potential and kinetic energies over here. It's called the Hamiltonian operator. And this looks like a pitchfork. It's called psi, psi from the Greek alphabet. Are solutions that allow the total energy of the atom to add up to the kinetic and potential energy of the electron. And it's also sort of like the electron acts as a wave when it's so small. And how can this wave particle thing exist in some way around the positive nucleus? It says the wave function psi describes the possible energy states which allow electrons to exist in a stable configuration around the positive nucleus. We won't go into the mathematics, it's way too much for us. Actually, it's not. If we had time to study it, you can do it, but we don't have time. It describes some geometries. That's the utility. Looking at what this psi thing means about where the electrons can possibly exist around the nucleus in these funky regions we call orbitals. These orbitals have geometries. There's another utility. It's more useful actually than psi itself. If you take that, square it, you get another number, a value that describes the likeliness or the probability of finding an electron in a particular orbital. And something like 95% chance that the hydrogen electron was going to be in the 1s orbital in the ground state. Maybe that means anything, maybe something, maybe it means something. There are several numbers that we'll look at in coming videos and lectures that allow solutions to this psi. One number is called the principal energy level. It's probably the simplest one. Call it n. N is an integer, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. That describes basically how close that orbital is to the nucleus. So if the positive nucleus is right in the middle, level 1 is just outside a little ways, level 2 is outside of that, level 3 is outside of that, level 4 is, forgive my crummy drawing, it looks like a junior high drawing, but it's the best I could do on short notice. Level 4 is closer to level 3, and level 3, I'm sorry, let's start over. Level 1 is quite some ways from the nucleus. The electrons are chilling here in level 1. In between level 1, n equals 1, and the nucleus, again, there's nothing. It's like outer space, even more void than outer space. There's no particles at all. No dust, no air, no nothing. Level 2 is actually closer to level 1 than level 1 is to the nucleus. And level 3 is actually closer to level 2 than level 2 is to level 1. And level 4 is closer to level 3 than level 3 is to level 2. So as you go out further layers, they get closer to each other. A couple of other numbers that we'll discover in coming videos: L, M sub L, and M sub S. These all kind of help describe solutions to this wave equation, psi, and the total energies available. In a way, for us right now, they're mysterious. They're labels, they're names for these places where the electrons can go. As we'll find out soon, let's say, for example, the L values actually have geometries. This geometry is L equals 1. These geometries are L equals 2. I'm sorry. This geometry is L equals 0. This geometry is L equals 1. This geometry is L equals 2. This geometry is L equals 3. And those have other names as well. S, P, D, and F orbitals. But in any case, I don't know if that helps or hurts. But thanks for watching, and I'll see you in class soon, or maybe discussion.